Bismillah ar-Rahman ar-Rahim. We discussed the magnetic flux. Now we are ready to discuss Faraday's law. That's the main subject in this video, okay, that we are talking about now. It says the magnitude of the induced EMF. Remember the induced EMF we talked about? In a conducting loop, it has to be conducting, of course. It has to be a loop, closed loop. Otherwise, you don't get anything. Is equal to the rate at which the magnetic flux phi b, this flux. Remember this flux here that we talked about? Yes. The magnetic flux through that loop changes with time. In other words, if you want to write it as an equation, this is the equation here. So you take that magnetic flux phi b, you take the time derivative, and you get the EMF. The minus sign here is not important for you now, because generally we always look at the magnitude of the EMF, the induced EMF. You can write here induced if you want. That's the induced EMF we're talking about, okay? Induced, which will produce the induced current. So this is important. The minus sign is related to the direction of the, actually the direction of the induced current. Remember, the induced current changes direction depending on the situation, okay? The current, the induced current, okay? Direction of the induced current, which is called the Lenz Law. This is related to Lenz Law, which we discuss later, okay? So this is volt, of course. The units is volt. It's an EMF, okay? And that, so you need to change the flux, the magnetic flux, the rate of change. As I told you here, the change of the magnetic flux can be either by changing the magnetic field, the strength of the magnetic field, changing the size of your loop, means by changing the area, size of the loop, or changing the angle by rotating your loop. This conducting loop we are talking about. Okay, so you need to have a conducting loop in our experiment. Okay, to do Faraday's law, you need the conducting loop. So the induced EMF is equal to the time rate of change of the magnetic flux. That's all. This is all what you need to do. Okay. If you have, that's the loop here. You can imagine that there is an EMF here. Okay. That's the EMF, plus or minus, and you have the induced current, okay? I induced and EMF induced, and you can calculate that EMF induced from that equation there, which is Faraday's law. This is Faraday's law, okay? That's Faraday's law. Faraday's law, okay? That's Faraday's law of induction. The induced EMF is equal to the time rate of change of the magnetic flux, and the minus sign, because this minus sign is due to the fact, we talk about it later when we talk about Lenz law, okay? Lenz law. Now, if you have n turns, more than one turn, okay, you have, your wire is actually made of many turns, n turns, so you have n turns, your coil has n turns, n turns, then your EMF, induced EMF will be, of course, induced EMF will be minus n d phi b over dt, where this is the flux, time rate of change of the flux through one coil, multiplied by n, the number of coils, will give you the induced EMF. So that's n for n turns, okay? When you have n turns, that's the Faraday's law for more than one turn your coil, okay? The coil which has more than one turn, okay? So again, I'm going to write down here, how would you change the flux, okay? Change in flux, because we are looking at the change in flux, time rate of change of the flux, magnetic flux. The change of phi b can be done, okay? Can be done by what? By, first of all, changing b, the strength, the magnitude of b, changing the magnitude of b. And this is, remember in the previous video, we talked about the change in magnitude of B by when Faraday was moving his magnet back and forth, okay? He was changing the strength of B, okay? The strength of B. So the magnitude of B, or you can change the size of your loop, changing the size of your loop by changing the area, by changing the size of the loop, okay? This is a change in area, okay? Change A, or by rotating your loop, rotating the loop, okay? Here you are changing, of course, change in the angle, okay? Change theta, okay? So that's how you be able to induce this EMF. And induced current will appear when you make one of these three changes, or two of them, or all of three, or all three of them, okay? This is how you would make your change in flux, and this will produce an induced EMF and produce an induced current in your loop, okay? That's Faraday's law. Now we can move to Lenz law to take into account the minus sign. But I told you, don't worry too much about the minus sign. We will always ask about the magnitude of the so we always do not worry, okay? Do not worry about the minus sign, okay? About the minus sign in Faraday's law, okay? Faraday's law. This sign is taken care of by the direction of the induced current. This sign is taken care of by the direction of the induced current. It's an indication, induced current. Okay, so the induced current will take care of the minus sign. Don't worry about it. Okay. So generally, we always ask about the magnitude when you're asking problems or examples. When we solve examples, we don't care about the minus sign. We care about the induced current. The direction of the induced current will take care of that minus sign. Okay. Okay. Let's discuss now Lenz law. Actually, Lenz law, it gives you the direction of the induced current. Okay, that's the direction of the induced current. Remember when I was explaining in the beginning, I said when we move the magnet toward the loop, this wire loop, the current is in one direction. When we move it away, the current is in the opposite direction, reverse direction. So the direction of the induced current is important to know it. So we use Lenz law for that purpose. What does Lenz law gives you the direction of the induced current in that loop. So it says an induced current has a direction, see the direction of the induced current. We're talking about the direction of the induced current here, okay? The direction that says that the magnetic field due to this current, because this current is going to produce a magnetic field, and that magnetic field opposes the change in the magnetic flux. You remember the Faraday's law, there's a change in magnetic flux. If there's a change in magnetic flux, there will be an induced current, and that induced current will produce a magnetic field due to the current which opposes the change in the magnetic flux. Very important. So nature doesn't want any change in magnetic flux. Imagine the magnetic flux through a certain loop, a certain wire loop was 10. Let's say 10 Weber, okay? Now you change the flux to make it 15. So nature doesn't want that increase by 5. So there will be an induced current in that wire, which is going to produce a flux which is minus 5. So that 15 minus 5 will give you 10 again, which is the original flux. That's the idea of the Faraday's law, okay? So there will be an induced current which will produce this. Remember that minus 5 flux is produced by an induced current, okay? So there will be an induced current at a direction that said that the magnetic field due to that current, the induced current, opposes the change in the magnetic flux. Now remember Lenz law, okay? We have the induced EMF, Faraday's law. We have the induced EMF, induced current, and the resistance. This is Ohm's law, okay? And Faraday's law, the magnitude of the induced current is n d phi over dt. So there will be a change in flux. And there was a minus sign here. That minus sign that we had before, it's due to the fact that it opposes Okay, the minus sign means it opposes the change in the flux. Okay, so I'm going to tell you, for example, the original flux is equal 10 Weber. Okay, let's say 10 Weber. So you change the flux. How do we change the flux, the magnetic flux? By changing the magnetic field, the strength of magnetic field, by changing the size of your loop, by making a rotation. Okay, you do these things. So you change the magnetic flux, and now change the magnetic field to, let's say, 15 Weber. Okay, so there's an increase of 5. So increase of 5 Weber in the magnetic flux. So there will be an induced current in your coil, so that that induced current, will give you induced B induced. So induced current I will produce an induced B, which will be going to produce a flux phi, which is minus 5 Weber. You see? Now, if you take this flux, which is 15, and you add to it the minus 5, you get back what? You get the 10 Weber, original 10 Weber, okay? So nature doesn't want, so total now, the total flux phi B through that loop is 10, you see it? So it was 10 originally. We make the change in the flux to make it 15, for example. So nature, we produce, there will be in that coil an induced current. Of course, the induced current means there's an induced electric field actually, which is going to move these electrons in your wire. Okay, and so there will be an induced current. So there will be induced electric field, induced current, induced EMF. Okay, which is going to produce an induced magnetic field, which is going to produce a flux. This induced magnetic field equal minus 5 to oppose this increase of 5. Okay, the increase of 5, it will be opposed. So the total flux will remain to be 10 Weber. That's the idea about this whole subject. I know this is not an easy subject, but this is the idea. Now let's do some practice about how to find the direction of the induced current. Okay, using Lenz law. Now imagine you have a coil like this, like this, flat. I mean, the coil is in the plane of your board, and you have a magnetic field. This is B, the external, is going to produce this original flux. There's a flux here, right? And that B external is increasing. Okay, let's say it is increasing. Okay, so there's a change in magnetic flux because of the increase in the external magnetic field. This magnetic field is due to, for example, you have a magnet, okay, and you are moving the magnet toward this coil. There will be an induced current in this coil, but to find the induced current direction, Lenz law, we have to know. I cannot find it until I have to know the direction of the magnetic field, which opposes magnetic field here, the induced magnetic field. Since this is increasing, remember now, my induced magnetic field will be in the opposite direction, will be in. So this is B induced. Why? Because it has to oppose the increase in the flux. There's an increase in flux. So phi is increasing here, okay? Increasing. The flux. The magnetic flux, phi B is increasing, okay? So there will be an induced magnetic field which is inside to oppose. It will create its own flux, and it will be opposite to the first one, because it will produce a flux just to oppose the increase, okay? Not more than that, just to oppose the increase. So if magnetic field induced is in this direction, we have to use the right-hand rule, remember, B inside, my induced current will be like this, okay? That's I induced, and that's Lenz law, my son. That's Lenz law, okay? That's so. To find the direction of the induced current, you look first at B external. Is it increasing or decreasing? If it's increasing, my B induced will be opposite to it. You use the right-hand rule to find the induced current. Okay. So let's now go to this example here. Another coil, different dimensions. Now my B external is also coming out, but now it is decreasing. I'm sure you should know that now the current will be the opposite direction, but let's see how, okay? If B is external is decreasing, means there's a decrease in flux, so there will be, here there's an increase in flux, but here there's a decrease. So my B induced will be in the same direction. So there will be a B induced. That's the magnetic field I'm talking about here. This magnetic field, which is due to the current. I'm not drawing the current, I'm drawing the magnetic field first, okay? B induced is out. If B induced is out, it means my current will be counterclockwise here. That's I induced. You put your fingers with the magnetic field, the blue one, the induced, and your thumb will be with the current. Look at this. From the current, the magnetic field rotates about the wire. So here it is out. So my thumb, here it is in. My thumb will go in this direction clockwise. Here, my thumb, it is counterclockwise. So here, phi is increasing because of the increase. Phi is decreasing here. So if phi is decreasing, the original phi, the original phi B, okay, is decreasing. So you have to increase your flux. So you have to put the magnetic field in the same direction. Okay, that's the idea of Lenz law. Another example, if you want, now you take your loop now, and you pass your magnetic field external is inside, and it is decreasing also. Is inside, B external. The green is the B external. Okay, that's the B external, and it is. Let's say it is decreasing. Okay. Can you, my son, tell me what is the direction of the I induced? You stop the video now yourself and try to use what we discussed here and try to find out what is the direction of the I induced, the current induced. Okay. So the way to do it, since B is decreasing, my magnetic field induced will be inside with the direction of B external, the same direction, because it has to oppose the decrease, so it has to be in the same direction to increase the flux. Okay, if it is in the same direction, then your fingers are with B, and then the current induced will be clockwise. This is I induced. Okay, so this is how, my son, this is how you find this example I showed you here. I'm changing the B. I can also change the size of the loop. Okay, increasing or decreasing. The same idea. If I have a loop like this, for example, let me take this loop here, okay? A loop of this size, okay? And my B external is inside B external, and I'm going to make the loop larger somehow. I'm going to make my loop larger. What do you think will be the direction of the I induced? Since B external is inside, and I'm increasing the shape of this loop, making it larger, it means I'm increasing the flux. So my B induced will be outside, opposite. That's B induced, okay? That's the B induced, okay? B induced will be opposite because I'm increasing the flux. Okay? So area is increasing, okay? Here the area, not B, the area is increasing, and my B external is constant here, okay? I'm fixing B here. I'm fixing the area, and I'm increasing B external. Okay. Here I'm fixing the B external. B external, I can write it. I can also write it here. It is still there, and it is constant. It's fixed, but I'm increasing the area. My B induced will be opposite. If it is opposite, my son, look at this. You put your fingers with the B external, induced, and then the current will be counterclockwise here in this figure here. That's I induced. Okay. Of course, you can draw now the EMF if you want. In this case, the EMF will be in this direction. The EMF, it will be like this. Okay, plus or minus. This is the induced EMF. Similarly, here you can put it. That's the induced EMF, plus or minus. Once you know the direction of your current, you know it goes from the positive to the negative. Similarly, here, that's my induced EMF. Induced. I hope this is clear, my son, related to Faraday's law and Lenz law. Faraday's law, this is Faraday's law here. And Lenz law, you have to use, you have to thing here. To find the induced current, you cannot find directly the induced current. You have to find the direction of B induced, then you find the induced current by using your right hand rule, okay? This is very important concept. I know it's non-intuitive things here, so you have to go, please, you have to go and practice, take all the exams, take problems from the end of the chapter in your textbook, and start practicing the direction of the induced current, and later we will solve problem related to finding this. Of course, this is Ohm's law here. This is the relationship between the E induced, the I induced, and R, which is the resistance of this wire. Thank you.